Electroanalytical chemistry plays a crucial role in the environmental remediation and water treatment applications. Good day, people. My name is Wandi Lengwenya. I'm here with my colleagues Lorraine, Peter. We will be taking you through photoelectrocatalytic degradation of emerging organic pollutants in water on an FTO BiVO4 NIS photoanode. Now, ladies and gentlemen, the presence of these organic pollutants in water systems, especially synthetic dyes and pharmaceutical companies, is a developing problem. Even at low doses, these pollutants are extremely toxic and persistent, like sulfur methoxazole. The aim is to develop an efficient photocatalyst for water treatment applications by fusing the optical and electrochemical characteristics of BiVO4 with NIS.
You are probably wondering what BiVO4, NIS, and FTO are. These are the materials that were used. As for bismuth vanadate, which is your BiVO4, and NIS, which is abbreviated for nickel sulfide, these were used for the composite of photoanode. And your FTO, which is your fluorine doped tin oxide, was used as a conductive substrate for the photoanode. Nickel nitrate hexahydrate and thiourea was used for the NIS synthesis, which is your nickel sulfide. Ethylene glycol was used as a solvent for the solvothermal synthesis, and polyvinylidene fluoride and N-methyl-2-pyrrolidine was used for preparing the photoanode slurry.
Of course, for these materials used, there is a method involved. Now, the synthesis of BiVO4 NIS composite via solvothermal process at 180 degrees Celsius for 12 hours. The coating of the synthesized material on fluorine doped tin oxide substrate to create a photoanode.
Then characterization using various techniques including X-ray diffraction and transmitted electron microscopy, then followed by the electrochemical and photoelectrochemical analysis using electrochemical impedance spectroscopy. Then lastly, the photoelectrocatalytic degradation experiment using 10 milligrams per liter solutions of rhodamine B and sulfur methoxazole.
To explain the results obtained from the photoelectrocatalytic degradation experiment, scavenger studies identified superperoxide radicals and holes as the primary contributors to pollutant oxidation. The photoanode's performance was influenced by pH, with acidic conditions favoring rhodamine B degradation and neutral pH for sulfur methoxazole. Stability tests showed consistent performance over multiple cycles. EDTA was used for scavenging holes, acrylamide for scavenging superoxides, and tebutoxide for scavenging hydroxyl radicals. Based on the percentage removal under the scavenger addition, it is evident that the major contributors are holes and superperoxide, as the degradation efficiency was 14% and approximately 24% when acrylamide and EDTA were added respectively. The hydroxyl radicals play a minor role in the PEC removal of RHB. As the removal percentage remained significantly high, the stability studies were conducted for 4 cycles for removal of RHB. The photoanodes were rinsed with the ionized water after every cycle that took 120 minutes and applied for the next trial with no prior drying or any other processes.
In conclusion, the photoelectrocatalytic degradation of organic contaminants using p-n heterojunction photoanodes, with the photocurrent response of FTO BiVO4 NIS being almost 7 times that of BiVO4 alone, the composite of demonstrated substantial improvements in charge separation and light absorption. Due to these improvements, organic contaminants were degraded more effectively, demonstrating the heterojunction photoanode potential for use in water treatment applications.
Would like to acknowledge the authors Dr. Tsepo Muhlala, Dr. Tunde Louis Yusuf, and Professor Nontlangabezo Mabuba. With the help of the Department of Chemical Science and Center of Nanomaterial Science Research at the University of Johannesburg. Thank you for tuning in. Don't forget to like, subscribe, repost. Thank you again.